So we are now at the presentation of Antoine. So we're shifting a little bit the topic. So up to now, we talked about the CALFAT approach. We talked about experimental work, and we'll go toward atomistic simulation. So it is really important in the context of the project that we have ingoing now to be able to use to our advantage supercomputer. So as most of you probably know, performing accurate and clean experimental work is difficult. Therefore, it takes time to explore many chemical systems, and each chemical system, they have their own challenges. Sometimes can be associated to a high vapor pressure, in other time it can be associated to a corrosion and the difficulty to keep the system at a higher temperature. And for all these reasons, we need to exploit the numerical approach that are also available. And one of the important tools for I would say, this century is atomistic simulation. And there are two branches of atomistic simulation. There are one based on ab initio method. So this is what Yavia presented this morning, where we're using the density functional theory to try to explore the energetic behavior of condensed phases. And there's another, let's say, branch where we're trying to use some fundamental physical ingredient to tune interatomic potential and then to explore these systems using molecular dynamics or Monte Carlo simulation. And Antoine will introduce you with this world of atomistic simulation, molecular dynamics simulation. So the floor is yours, Antoine.
All right, thank you very much for the introduction. Can you hear me well and see my screen?
Yes.
Perfect, awesome. So GP did a great introduction, so I'll keep it at that and just go right away to my presentation plan. Basically, it's going to be pretty simple. I'll be going on a brief return on my scientific interest, which I presented last year, as well as the advancements on what I had presented last year. Present you some simulation results on what we're working on right now and our future work and what we're planning in the future. Alright, so about me and my scientific interests. I have a bachelor's degree in engineering at Polytechnique, and I'm currently doing my master's, as GP has said. My interests are basically in atomistic simulations as well as in numerical models, ideally in using both in the use of informatics inside the field of chemical engineering. The context of my master's thesis is working on the aluminium zinc chromium system, which is part of the 7000 series of aluminum alloys. It was first created by Alcoa in 1943 with the 7075 series of aluminum alloys for this specific plane. For your interest, this is the phase diagram of the aluminum zinc. Why am I showing aluminum zinc first? It's because zinc is the main alloying element that defines the 7000 series of aluminum alloys. The goals of my project are basically to develop a molecular dynamics simulation protocol to be able to identify the impact of the primary phases, then get a better understanding of the mechanics of phase change through those simulations. And then one of the goals we had was something that GP was always wondering about, was whether or not it was possible to obtain the solidus liquidus curves of a multi-component systems using only molecular dynamics. A bit more complex of a phase diagram in this system, which complexifies a bit the project, is the aluminum chromium part of it, because chromium encourages the formation of intermetallics, and this is why we're focusing on this in this project. Alright, so let's go to the simulations. One of the first things that we evaluated was the impact of the binary distribution for the simulated alloys. So in this case, we have 3 different samples. All of them are 75% aluminum and 25% zinc. The gray bubbles represent aluminum atoms, while the orange bubbles represent zinc atoms. So I went from a simulation that was completely demixed on the far left to random at the middle to perfectly ordered in an L12 fashion at the right. So let's see the effects. Here's a graph. So the main importance of the graph here is the one at the bottom left, where you can see the enthalpy is a function of temperature. So the basic figures that I showed you earlier are associated with these curves. And the thing that's important in this graph is this little jump here in enthalpy, which is signaletic of phase change. What's interesting here is the temperature at which this jump happens, because this gives us the melting temperature obtained through those simulations. And as we can see, as a function of the initial distribution of atoms, there is a clear impact on the melting temperature. All of them, you'll notice, are slightly offset from the actual melting temperature we're expecting, which is the dashed line right next to it. Another impact that we've noticed is in the impact of the vacancy distribution. So this is an extreme example, but as you can see, again, with these three systems that are simulated, there is a huge impact on the results as well. So this is why we're trying multiple methodologies to see how the vacancies will have an impact and how can we use them properly. So now I'll explain more what's the idea behind vacancies. When you make simulations to identify the melting temperature, the simplest one but the most inaccurate one is using a perfect lattice. So basically that's just a perfect lattice and you run it until it melts. The problem here is that its melting temperature will be its thermodynamical melting temperature rather than its mechanical melting temperature. This means that it will be higher than what would be expected, because in real life the alloys or metals that we melt have impurities or imperfections that reduce their melting temperature. This is why we use methods such as this one, the random porosities, in which we poke holes randomly inside the lattice in order to decrease the melting temperature by creating imperfections inside the simulated lattice. Using random vacancies is the most reliable one amongst the different porosities methodologies, but it's harder to reproduce due to the randomness of it. Another methodology is using perfectly ordered vacancies. If you look at the left of the simulated box, you'll notice that there are rows in an L12 fashion in which there are missing atoms. This is where the atoms were removed through the simulation protocol. There's another similar method, which is using a periodic boundary vacancy. In this case, if you look at the left, you'll see that there's a chunk of atoms completely missing, whereas all the rest is perfectly fine. The simulations use periodic boundary conditions. So in this case, this means that the vacancies will have an effect infinitely, we'll say, in the simulated lattice. Another method is using a single vacancy, which would be a hole inside of the entire atom, in which we will avoid creating periodic boundary conditions vacancies like beforehand. So what we're doing right now is evaluating the impact of each of them. I would like to show you results, but they're running right now on supercomputers, so I can't give you results as of yet because I don't have them right now. Another methodology for evaluating the melting temperature is the interface method. It's more computationally demanding and it takes longer to run. However, it's much more accurate, and this is why it's the standard in literature. So here are the basic steps. First off, you create a big simulation box and you heat up half of it. The idea behind the interface method is that when you create a liquid and you have the interface between the liquid and the solid, you will make it so that the simulation will have an easier time melting due to the presence of that liquid phase. So you have to heat up half of the simulation box at a much higher temperature than would be expected for the melting temperature to ensure that it liquefies, and then you bring it back to the normal temperature and just equilibrate it for a long while after some isobaric expansion to equilibrate the system. So here's a quick video so you can see a bit more how it works. Focus at the bottom of the lattice. You will see that during the isobaric expansion, even though the bottom half doesn't change its trajectories, it expands due to the change in temperatures. And now from now on it's just equilibrating until it reaches the appropriate energy. And when we plot the enthalpy as a function of temperature, we'll notice a jump again, despite the fact that there's an equilibration between liquid and solid. Another method that we're proposing, in this case for multi-component systems, which we believe is very interesting, is the interface method, but this time with compositions. It works with the same idea as the interface method I just presented. However, instead of creating an interface between temperatures, we're creating an interface between compositions. This method has never before been seen in the literature, and it's completely new from us. The global idea here is that, look at the two examples. On the one on the left, the top side of the simulation is the solid phase, which, as this phase diagram indicates, should be approximately 73% of the composition of the sample at 59% of aluminium. As you can see, this is pretty much the case, whereas for the other example, the liquid phase is much bigger. The idea here, as I said, was to match the compositions of each phases and see how it would behave in a simulation. The results are very promising, especially for simulating the solidus line. As you can see in this phase diagram, around the eutectic it's even more accurate. The reason why we believe it's so good at evaluating the solidus line is that, as you can see in this video, the liquid phase melts first, which then triggers the solid phase to melt. Here, the two lattices are the exact same. However, on the left you can see the atom types, again, white being aluminium and orange being zinc. And on the right, you can see the local ordinancing of the atoms. So in green, it's FCC, as the alloy should be. So basically, if it's green, you can believe it to be solid. And once it starts changing colors, it's because it's progressively melting. Alright. Notice how the simulation started melting from the bottom and then to the top, which was starting from this liquid phase into the solid phase. Another methodology that we're proposing is the grain method. This is also never before seen in the literature. And the idea here is that we create a stupidly big lattice and create grain defects inside of it, as you can see in this picture. So notice how the different FCC structures are aligned differently and are joined by grain boundaries which are not in FCC. The idea here is that those grain boundaries will make it so that the melting temperature will be lowered. Here's two example videos so you can better understand the idea behind the simulation. On the left, the simulation is below the melting temperature. Notice how the grain boundaries dissolve into the FCC lattice. The second video is above the melting temperature. Notice how, in this case, the melting starts from the grain boundaries. The thing right now is that we're optimizing the methodology to find the right surface to volume ratio. Right now, the grain boundaries are too effective, and even with big systems, we're underestimating the temperature of melting. So to better understand this graph, I understand that it's a lot to take in at first. The color indicates the temperature, and on the y-axis it's the enthalpy. So this is what we're using to identify whether or not it is at the liquid phase. On x it's the dimension, the size is the size of the grains. So right now, as you can notice, a lot of simulations which would normally be at a lower enthalpy are right now above, which means that the temperature of fusion is underestimated. What we would want would be for that point, for example, to be lower, because that point is right around the melting temperature. And so when we can evaluate it at an enthalpy identifying of a solid, this would indicate that we're appropriately identifying the melting temperature through the grain method. Right now, the grain method is actually identifying the melting temperature of nanosystems for nanoscale grains, because these dimensions are really big for molecular dynamics, being at approximately 0. We're at the nanoscale basically, which is much bigger than molecular dynamics usually are. To better identify the sweet spot between the surface to volume ratio, I'm studying the surface area, let's say, of the grains, as you can see at the GIF at the bottom left. And so as you can see in this graph, we're quite plateauing right now, which I believe is a good sign, because even though we're plateauing in the surface to volume, the colors are progressively going towards the blue, which is what we want, because the darker the color, the lower the enthalpy, and so the closer we are to being at a solid state. Alright, so for the upcoming work, basically, it's only now finishing up simulations and going through the results, as well as different papers. So here's a picture of Beluga, the supercomputer we're working on, and thanks again to Compute Canada for lending us those resources. Then working on papers. So the first one would be on comparing the different melting methodologies, invariably of chemistry, and then adding the impact of solidus liquidus, as I showed you before. And then the third one is using grain defects. So I censored this picture so your computers would not be scared, because this has millions and millions of atoms and takes hundreds of CPUs to run. But I hope they're ready now. This is what it looks like. So as you can see, again, grains are pretty big, and this is why the system are pretty heavy to run. So I hope you enjoyed the presentation. If you have any question, please feel free to send them. And another big thanks to our industrial partners for supporting us in this project. Thank you very much.
Thank you, Antoine. So I think it was a really nice presentation, and what we could see at the toward the end is that we are not yet at the level of the macro scale where we can have all these metallurgical features that are important to describe the physical metallurgy of an alloy, but it looks like we're slowly getting toward a critical size where the surface energy is not impacting too much the melting of pure elements or alloy, and therefore this is a sweet spot where we're going to be able to obtain useful thermodynamic information in the future for system where we don't have any thermodynamic information. So it looks promising, and thanks to Compute Canada, we can now run the simulation at the almost nanoscale size. It's still pretty small for a metallurgical application, but positively, if we're able to converge toward a value that seems to match the one that we have for bulk material, then hopefully we can use that scale to obtain useful thermodynamic properties for the development of our database. So thank you again, Antoine. Let's move on to the next presenter, which